Welcome back to EGE 2013 Statics, and I'm Professor Jim Kearns again. We're going to talk about the equilibrium of a particle and some free body diagrams, and as we run through a two-dimensional example where all the forces are coplanar or in the same plane, making this a two-dimensional problem. First, let's quickly define a particle. A particle over here on the right is an object that is free to translate or to move up and down, right and left, any direction like that. But a particle does not deform, and a particle does not rotate, okay? It does not, we don't consider rotation or torques and things like that. So we're just straight forces on this, and that's what distinguishes a particle from a rigid body, is the lack of rotation. Works in simple translation. So since it's only free to translate, it does not rotate, we know from our, statics is a case where the sum of the forces is equal to 0. We know that the only forces we need to consider, and they're vectors of course, is the forces in this two-dimensional case are forces in the x direction, forces in the y direction. If it was a 3D problem, there would be z as well. Okay, so there's our conditions here that we need to achieve, the summation of the forces x, sum of the forces y equals 0. And if we look at our problem over here on the left, we see we have a 10 kilogram weight hanging from this ring that I've labeled R, and we labeled that C. I have a cable A that connects that ring to some solid wall. I have a cable B that takes it over a pulley, a ideal frictionless pulley, and is attached to some unknown mass. And when we look at our problem, we see we have 1, 2, 3 unknowns, but we only have 2 equations. It's a bit of a problem, eh? Well, not really, because we can take part of our problem here. Let me pick a color. It's okay. I can take a piece of our system right there, that ring itself, cut that out virtually, not literally, and draw a free body diagram of all the forces acting on that particular particle, and that's the diagram over here. Okay. I see in that diagram I have, I had my answers already written because I'm re-recording this because I hit a bug in the last one. Okay, looking at the free body diagram, I see that I have 1, 2 unknowns, and I have 2 equations, so this should be nicely solvable, right? Okay, so let's start with that. Let's start by writing the equations that we know. Let's write everything we know, step 1. Back to my pen. We'll do them in alphabetical order here. I can say that my force, my A vector, the A force, and that is equals AX, and there is no Y component. This is drawn as a horizontal cable. That's the end of it. B, which is my green color, B equals, well, there'll be some unknown B sub X plus B sub Y. And for my C, there is no X component, so there's only, well, it's 10 kilograms times the acceleration of gravity, 9.81 meters per second squared. So I have 98.1 newtons. Okay? So, looking at these, since I can separate my X equilibrium from my Y equilibrium, if I look at this here, I see that the sum of forces in the Y direction, I have 1 equation, 1 unknown. That's pretty easy to solve. So, sum of the forces in the Y direction is equal to 98.1 plus by equals 0, and that tells me that or actually minus 98.1, right, because it's acting downward. My mistake. Okay, so it tells me that by equals 98.1. Okay, now from geometry, I know if by is equal to, oops, I'm drawing x, aren't I? If I know that by is equal to 98.1, I can calculate b from that force and that angle. So I know that by equals b times the sine of 30. And given that, I can determine that b is in fact sine 30 divided by by, or by divided by sine 30, so that's over 0.5, and that's equal to 196 newtons. Erase that. So I know that's 196 newtons. Now if I know b, I can calculate bx, because bx is just going to be simply b cosine of 30 degrees, and that's going to be equal to 170 newtons. So I can substitute that in up here, and this is, I should have put in the i's and j's, I'm sorry. 170i, and what did I say? It was 98.1 j. And now I can look at the x-axis equilibrium, and I can say that the sum of the forces in the x direction equals 0, equals, I have 170 from b plus a x equals 0. I already have the 0 in there. So I can say that a x equals minus 170. So that's 170 pounds pointing to the left. So there we go. I've got all the forces acting on this connection here, this ring. I have x components, y components, everything I need. So now I've solved 2 out of my 3 unknowns. Now I just need to solve for my mass. Let me slide down a little bit. Okay, well, if I draw a free body diagram of my pulley, right here, I end up with this, and I know that I have a force B, which is 196 Newton, and the property of a pulley with a cable going over it is that the tension on either side of that pulley is going to be the same. So by inspection, I can tell you this is 196 newtons there. And if I look at a free body diagram of my mass, I have 196 newtons force in the cable. So obviously, for the sum of forces to be equal to 0, I need 196 newtons from gravity. Dividing that through by the 9.81, I get my mass is equal to 20.0 kilograms. And now I've solved my equations. I've found all the forces, all the tensions, and all the cables. I found out what mass is required to keep that in equilibrium given that geometry. Obviously, if we change the mass, if we increase the mass, then it would just change the geometry, right? A larger mass would probably pull this up and change these angles. This would no longer be horizontal and different things. But given the geometry, that's our solution. And thanks for watching. Hope this is helpful.